These are notes on accuracy and precision, and they are found in 3.1, Chapter 3, Section 1 of your book, right before the significant figure stuff that you've already looked at. So accuracy and precision have to do with data collection and measuring. They're important aspects in the collection of data and when taking measurements from equipment. So we're going to talk about the difference between those two words and then how we apply them to actually taking measurements from equipment. Accuracy and precision are not unrelated topics, but they are different aspects of measurements. So the best results come from being both accurate and precise. Let's look at what these words mean. Accuracy, when you're talking about the accuracy of a measurement, it's talking about how close a measurement that you take is to a known value. This means you only need one measurement to talk about whether you're accurate or not. This is different from precision. In precision, you need a number of measurements to decide if you're precise. But with accuracy, you can take one measurement, compare it to the known value, and then determine whether you are accurate or not. If you do have multiple data points, so you take, say, 3 trials, you usually compare your average of those trials to the known value to see how accurate you are. So for an example, in an experiment where you're determining the density of water, the student, you, calculate the density to be 0.95 grams per milliliter when the actual density of water is 1.0 grams per milliliter. You were pretty accurate. You got pretty close. You're only off by 0.05 grams per milliliter. Precision is a little different. Precision comes from how close a series of measurements are to each other. So you need more than one measurement that you've taken in order to be precise. As an example, let's say when, again, you're determining the density of water and you repeat the experiment 3 times. And your 3 trials, the first one you get 0.96 grams per milliliter, the second one you get 0.94 grams per milliliter, and the third one you get 0.95 grams per milliliter. All of these measurements are close to each other, and so we would say they are precise. Now they also happen to be close to the actual density of water, and so they're also accurate. But there are times when you can be very precise, but if you're not close to the actual, then you're not being accurate. So a lot of times people use a bullseye to give you a visual on accuracy and precision. So in this first target, you have your 3, I guess this is a dartboard, you have your 3 darts all over the place and they're not close to the bullseye. So you'd say there's low accuracy because you didn't get close to your target, and low precision because your 3 darts are all over the place. In this second dartboard, you can see the 3 darts are clustered very closely together, but they're not close to the bullseye. So here's a case where your accuracy is low, you weren't very accurate, but your precision was high. This may happen where your tool isn't calibrated correctly. So it's giving you measurements that are close to one another, but because it's not calibrated correctly, they're very far off from what you should have gotten. This would be considered high accuracy and low precision. So you can see all the darts are close to the bullseye, but they're not in the same range as each other. So this is a case where perhaps by averaging your data, you're getting close to what you should get, the known value, but you're not at all precise in getting that. You're not repeatedly getting the same thing. So this may be a little of luck. You know, certainly if you get 0 one time and 100 another time, that's going to average to 50, but neither time did you get actually close to 50 if 50 is the known value. And then here, this is obviously what we aim for. This is high accuracy and high precision. All of the darts are clustered together on the target in the bullseye. So that's obviously the best case scenario. So here's an example. A student is measuring the density of copper. She gets 3 measurements, 6.37 grams per milliliter, 6.34 grams per milliliter, and 6.30 grams per milliliter. Copper's known density is 8.96 grams per milliliter. So analyze her data and determine if she was accurate, precise, both, or neither. Go ahead, pause the video, take a few seconds to think about that, and then continue. You should have gotten that she was precise but not accurate. So all of these measurements were very close together, within hundredths of a gram per milliliter. But they weren't close. If you average them out, they weren't at all close to copper's actual density of 8.96 grams per milliliter. So we can say her measurements are precise, however they are not accurate. And accurate is a matter of degree, certainly. How close do you need to be considered accurate? Sort of depends on percent error. So we'll talk about that in a minute. Let's first, though, look at, when using measurement tools, how many decimal points do we mark them to? So the rule of thumb is you measure to 1/10 of the smallest marking. So in this first graduated cylinder here, the smallest marking is 1 milliliter. If you look at that, you notice that the increments between the 50 and 60, there's 10 of them, so each one of those is a milliliter. And so we record to the nearest 0.1 milliliter. That's going to be an estimate, so different people may determine that 0.1 differently because it is an estimate. So remember, with a graduated cylinder, we read from the bottom of the meniscus. So we can all agree that this is at least 52, and then I'm going to estimate that it's 52.9, that it hasn't quite gotten to 53.0 yet. And you would write it for significant figures. If you said, no, this looks like 53, you would say 53.0, so that we understand that that tenths place is an estimate. You can't go any further. You can't say, I think it's 52.99, because the 0.9 was an estimate. It's not marked, and you can't put an estimate on an estimate. If you look at this second graduated cylinder, in this case, there are 10 markings between 6 and 7, meaning the smallest marking is actually a tenth. So we're going to record to the hundredths place, and that hundredths place would be an estimate. So we can all agree, again, that we've got 6.5. Some of you may say this is 6.60. I think it looks more like 6.59. But again, we're recording to that hundredths place. And then this is also how we're going to get our limit of precision, our significant figures for then, if we're doing, let's say we're taking 3 volumes and then we're averaging it, now we know, okay, how many places are we going to record the average to? So let's look at percent error. Percent error gives us a better idea of how accurate we are, and I'm going to show you some examples of why that is. So percent error can be used to determine how far from an actual value the experimental value is. Or another way of saying that is, percent error helps to tell you how accurate your measurements were. It's not telling you how precise. Precise is looking at the range between the measurements. This is telling you how accurate. And the equation is the percent error is the experimental value that you calculated. In some cases, you'll see this is labeled the calculated value, minus the actual value, the known value, or in some equations you'll see it as the theoretical, divided by the theoretical, times 100%. And in this case, the percent is more of a unit, so you're not figuring out 100% on your calculator. In some equations, you'll see the absolute value sign around the experimental minus actual. I choose not to include that, and I'm going to show you why in a second, but just know that you may see that it doesn't matter if it's negative necessarily, although the way I view it, I think the negative is very instructive. So here's an example. Water's known boiling point is 100 degrees Celsius. A student is asked to determine its value experimentally. The student's thermometer reads 98.9 degrees Celsius when the water is boiling. What is the student's percent error? Go ahead and calculate that. And so pause the video, calculate it, and then check your answer. This is how you should have set up the equation. 98.9 minus 100 divided by 100 times 100 equals. And so if you do this on your calculator, and one thing to know as far as percent error, you need to do the subtraction in the numerator before you divide. So you should have gotten negative 1.10%, or if we're talking absolute value, it's 1.10%. Three significant figures because the 98.9 has three significant figures. The reason I like to include the negative is because it shows you that your measurement was actually under what it should have been. Here's another example. A certain cell has a diameter of 2.2 times 10 to the negative 2 millimeters. A student measures the cell and calculates a diameter of 1.22 millimeters, which is clearly very off. What is the student's percent error? Go ahead, pause the video, calculate that out. So you should have set up your equation like this, and then your answer should have been 5,400% off. And again, it's positive because you were larger than the actual. Now I gave you these two examples because the difference between the known and the actual, or the known and the experimental, if you just subtract, is the same. It's about 1.2. In example 1, you were off by about 1.2 degrees. In example 2, you're off by approximately, it's not exact, 1.2 millimeters. So you're off by the same amount, but because the thing you're comparing to is so much smaller in example 2, that 1.2 millimeters is actually off by 5,400% compared to the 1.2 degrees, which is only off by 1.10%. This is why percent error is so instructive, because it gives you, it not only tells you how far you're off, but it compares it, it gives it as a fraction of what it should have been. Please make sure you ask any questions on the comment section or bring them to class.